I said it was easy.
Okay, just a little review of the unit. Basically, we're going to be solving first degree, second degree trig equations. And then we're going to be looking at some identities and how to prove those. But for starters, we're going to take it easy. We're just going to review something you guys already know. And this will be good review for your unit test, which is now on Tuesday, not today. So this is something you guys should already know, so I'm going to ask for your feedback. If we had to solve for sine x equals -1/2, how would I figure out the value of x? Okay, what value of x could we plug in there so that we'd get -1/2 as the solution? You guys remember the steps? Very close. So the second step is we need to find a reference angle. Okay, so we're going to get x equals second sine, and instead of putting -1/2, we just put 1/2. What's the negative going to tell us? No, because we're not talking about angles. This is a ratio.
Quadrant.
The quadrant. Good, and that would be the first step. Okay, so quadrants. Okay, so using our cast rule, if sine is negative, that means we'll have a solution in quadrant 3 and in quadrant 4. So we're going to have two solutions to this. So now that we know the quadrant and we know the reference angle, we can apply the reference angle in those specific quadrants. Quadrants 3 and 4. Okay, so if you guys solve for the reference angle, what do you get? Is it 30 degrees? Just remembering my special triangles, I know sine would be a y value. And 30 degrees would be my special triangle to get a y value of 1/2. Okay, so, or you can just plug it in your calculator and get second sine, 1/2, you should get 30 degrees. Okay, so we know the reference angle, and now let's apply that in quadrant 3. So going from 0 to that terminal arm, we have 180 plus 30 degrees, that's 210 degrees. And then we need to apply our reference angle in quadrant 4. So we'll go 360 minus 30, and we get 330 degrees. Now, one thing that we need to pay attention to is our domain is in radians, so we should probably state our solutions in radians. So if you guys convert 210 and 330 to radians, what do we get?
7 pi over 6.
So 7 pi over 6,
11 pi over 6.
and 330 divided by 180, we get 11 over 6 times pi. Okay, so these are our two solutions. And if you guys want to make sure that these are your solutions, you can go sine 210, press enter, make sure you're in degree mode if you're using 210, and you should get a ratio of -1/2. If you don't get that, you don't get left hand side equals right hand side, then the angle you solve for is incorrect. Okay. So let's just practice again. One thing that's important is you always need to isolate your trig ratio. So let's isolate secant x first. So we're going to add 5 to the other side, and then we'll divide by 3 on both sides. Reciprocal of secant is cosine. So if we just take the reciprocal of the ratio on the right hand side, we'll get cosine x equals 3/5. And we'll go back to our first two steps where we're figuring out the quadrants and the reference angle. So cosine is positive, which means we'll have solutions in quadrant 1 and quadrant 4. Okay, and the reference angle will be second cosine, 3/5. You guys can help me out when you go second cosine 3/5. 50, so to the nearest degree, we get 53 degrees. Okay, so that's our reference angle. Now let's just apply that in quadrants 1 and quadrants 3. So in quadrant 1, that's pretty straightforward. It's just a rotation angle at 53 degrees. And in quadrant 4, our reference angle is 53. So to get our rotation angle, we have to go 360 degrees minus 53 degrees. We get 307 degrees. So two solutions, x equals 53 from quadrant 1 and 307 degrees from quadrant 4. So the solutions that we found in part A and part B, they're solutions within 2 pi or 360 degrees. It's basically just quadrants 1, 2, 3, 4. But as we know, the graph of sine and the graph of cosine, I'll just do sine, it's going to keep going and going and going and going. So there could be endless possibilities of solutions if our domain goes beyond 360 degrees, or if it goes beyond 0 degrees towards negative infinity. So that leads me to the general solution. General solution is basically the solution when the domain is all real numbers. Okay, there's no restriction between 0 and 360 or 0 and 2 pi. You'd find solutions to infinity, basically. So let's just explore a graphical approach on how to solve this exact same question, and then we're going to lead into finding infinite solutions. So the first method we're going to look at is the x-intercept method, and for that method we have to make sure that the entire equation is on the left-hand side of the equation. Okay, so if we have sine x equals negative 1/2, we're going to have to add the 1/2 to the left-hand side, which gives us sine x plus 1/2. Okay, so if you guys could just throw that into your y equals, please. And there's also some recommended window settings there for us too. Okay, now looking at the domain, it's 0 to 2 pi, and the window settings are in pi measurements. So what mode should I be in? Radian, good job. Okay, I already am. So I'm just going to change my window settings from 0 to 2 pi. With a scale of 30 degrees or pi over 6. And on the y-axis, we'll have negative 2 to 2 with a scale of 0.5. And then, once we have our window settings, go to y equals, and then put in sine x plus 1/2. Always make sure you close the brackets before you add a constant beside. Okay, then we can graph it. So any guesses what our solutions will be for using the x-intercept method? It will be your x-intercepts. So we can just trace this x-intercept and this x-intercept. We'll do one at a time. Second trace, number 2 for your zeros. Left bound will be above, right bound will be below the x-axis. Okay, we're getting 3.66519114. The x-intercepts, or the solutions that we're going to be finding, need to be in terms of pi. So a little shortcut to figure that out. I'm just going to quit out of my graph. Press X. There's the decimal you guys just found. Now we can divide that by pi. This will be the fraction that we multiply by pi. So I'm going to go math, enter, enter, and it's 7 pi over 6. So that's my first solution within 0 to 2 pi. So just to clarify, this was the x-intercept.
Which one first? What was that?
The one on the left.
Really?
Yeah.
That's not what I got.
Okay. Then you want to divide pi out of there, and that will be the fraction that you multiply by pi. Just take a moment, solve for the second y-intercept, or sorry, x-intercept. So you have to close the bracket before you add the half. It's just sine of x. That looks better. Thank you. So, just a troubleshooting, one student, they didn't put their brackets around the x, they put it at the end, so it just caused you to get the wrong graph. So please just make sure that you close off the brackets before you add your vertical displacement or your constant. Yeah.
Excuse me.
Hey. Choose your mouth open. That's all. You want to mark it?
So then if you're still not getting the right graph, you should always double check what mode you're in. If your window settings are in radian measurements, then you should be in radian mode. Okay? So if we went and traced our next x-intercept and then we divided by pi, you should have gotten 11 pi over 6. Okay, does anyone want me to walk you through that visually? We're okay? Son, you want me to? Yeah, okay. So second trace, number 2. And now I'm just going to find the far right x-intercept. Okay, so that's left bound, press enter. And I'm going to go right bound, press enter again. And I get 5.75, etc. Now I need to take that value and put it in terms of pi. So I'm just going to quit out of the graph and press X. You see how it's the same decimal? Divide that by pi. And this will be the fraction that's multiplied by pi. So go math, enter, enter, and you get 11 over 6. Got it? Okay. Good. So those are our two solutions within 0 to 2 pi. You guys drew a sketch as well? Okay, awesome. So now what we're going to do is we're going to take that same graph, but our domain has changed. We're looking now for solutions between negative 2 pi and positive 4 pi. Okay, so let's just adjust our window settings. Negative 2 pi to 4 pi. The scale stays the same, it's still pi over 6, and the y measurements, y min, y max, and the scale are going to stay the same. So as you can see, we're crossing the x-axis a few more times. I'm just going to highlight the x-intercepts that we've already found. Okay, this is 7 pi over 6, and this is 11 pi over 6. Okay, those ones we've already found, but there's 1, 2, 3, 4 more x-intercepts within now this new domain. So we need to solve for those. But maybe it doesn't have to be so complicated as tracing all these x-intercepts. Maybe there's a rule behind this. And hint, hint, there is. So let's just look at 7 pi over 6. If I were to go through one period, I would end up here. Okay, what is the period of the sine graph? What's
2
the,
pi.
Yeah, 2 pi, right? So basically the new x-intercept will be 7 pi over 6 plus 2 pi. 7 pi over 6 plus 2 pi. So I can calculate this just on the side here. I need a common denominator. So I get 7 plus 12 is 19 pi over 6. Okay, that's my next x-intercept. Now, if you forget this, of course, you can just trace your x-intercept, divide the pi out, and you'll get 19 pi over 6. Okay, what do you think moving in the negative direction? So let's go back one period. How will I find this x-intercept? Good, you're going to subtract. So we have 7 pi over 6, and I'm going to subtract 2 pi. We need a common denominator, so multiply by 6 in the numerator and denominator. And we get 7 minus 12, that's negative 5 pi over 6. So just from 7 pi over 6, I've now found my 2 other x-intercepts. Okay, but if you count in total, there's 1, 2, 3, 4, 5, 6. So we found 2 other ones from using 7 pi over 6. I can find 2 more by adding or subtracting a period from 11 pi over 6. Okay, but let's just do this algebraically. I'm going to break up the class a little bit and just divide who's solving for what. So these are the 4 x-intercepts we need to solve for. I've already given the answers for 2 of them. 1, 2, 3, 4. We already know those 2. So I'll get first 4 up here. You guys can solve for the first one. Okay, Jane, Hannah, Chris, Nolan, Mike, you guys can solve for the second one. You two solve for the third one. And I'm not doing this evenly, obviously. Okay, and Stan and Dawson can solve for the fourth one. Okay? Pardon? So you can do this using your calculator. You just need to trace the x-intercepts. Okay, so second trace, 2 for zeros, divide the pi out, and get the fraction with the pi. Okay, so you need the x-intercepts in terms of pi. If you need a hand, I'm coming around. Need a hand? Oh, no, we're good. You're good? Okay, so
No, wait. Do I have to write the answer up on the board? It's 2 pieces. I can solve for the rest of them, or
just
just the one? Just 3? I think I got the answer.
4 acres, right? Mine up there.
What is it?
Negative 5 over 6.
What one were you?
1.
1? Wow. Is that what I was supposed to do? I was 19.
we had the second one. What did you get, Hannah? Negative 5 over 6?
My bicycle is phenomenal.
It really is. It's much better than mine. And the fifth group,
23 pi over 6.
23 pi over 6. Okay, so let's just record our solutions. We had negative 5 pi over 6, negative pi over 6. Don't forget that we originally had 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6.
I know. That's one. Yeah. That was you. Nice guy.
So good work, everyone did awesome. You're welcome. Okay, I'm just gonna throw out an observation. If you look at 7 pi over 6 and 11 pi over 6, what is the difference between the numerators? 4. Okay, and let's look at this pair here. What's the difference? 4. 4. The difference between 19 and 23? 4. Okay, so because the period is 2 pi, these differences should be consistent with the pairs of x-intercepts. Okay, so for every 2 pi, those pair of x-intercepts should differ by the same amount. Okay, let's talk about a few other relationships. I've already pointed them out, but I'll identify them again. So if we were to look at negative 5 pi, 7 pi over 6, and 19 pi over 6, what did they differ by? So in other words, boom, boom, boom. What do they differ by? 2 pi, 1 period. Okay, and we can see that this is 1 period.
No,
This
you
is
were
2
right.
periods.
No,
Okay, so all the x-intercepts from 7 pi over 6 will differ by 2 pi. Okay, now let's look at negative pi over 6, 11 pi over 6, and 23 pi over 6. Okay, so these ones here. What do they differ by? 2 pi. Okay, so for part C, that's basically what we're summarizing here. So all the solutions derived from pi over 6, they differ by 2 pi. And those ones would have been negative 5 pi over 6 and 19 pi over 6. And for 11 pi over 6, the ones that were derived by adding or subtracting 2 pi were negative pi over 6 and 23 pi over 6. So if we needed to find solutions going from negative 4 pi to 6 pi, okay, originally our domain, what was it just above, is going to negative 2 pi. So how would you get to a domain that would be between negative 4 pi and positive 6 pi? What could you do with your solutions? Okay, you could add 360 or 2 pi, or you could subtract 2 pi. So the furthest solution on the left was negative 5 pi over 6. Okay, if we subtract another 2 pi, we will get a solution that's within that domain. Okay, so we need a common denominator. We have negative 5 pi minus 12 pi. So we get negative 17 pi over 6. And if I go 17 divided by 6, I get 2.83 repeated. Let's just see if we can go further. So let's take this one now, and let's subtract 2 pi. Okay, if I go 17 minus 12, what do I get there? Sorry, negative 17 minus another 12. Negative 29 pi over 6. Let's just check that. So negative 29 divided by 6, I'm getting negative 4.83 repeated pi. Is that outside of the domain?
Yeah.
Yeah, so I've gone too far. This one cannot be part of my solution. So you guys can just put an X through it and explain that it went too far. I was just going to erase it because it doesn't fit in. Okay, so you can cross it off or erase it. So you can just test, did you go too far or not? This one fits it within the domain. If I went one more rotation, it wouldn't have. Alright, so this was the one that was furthest to the left. What was the x-intercept that was furthest to the right? 23 pi over 6. So we're going to add 2 pi. Get a common denominator. So we have 23 plus 12, 35 pi over 6. Okay, and let's just check it. 35 divided by 6. So you get 5.83333 repeated, basically. Okay, that fits before, it fits within the domain, before 6 pi. If I added 2 more pi, I'd definitely be out of it, because 5.83 repeated is pretty darn close to 6. So I know this would be where I'd stop. Okay, so these are 2 more solutions. Good stuff. So if I were to expand on this idea of adding 2 pi or subtracting 2 pi, I could come up with my general solution. Okay, our first solution within the period of 0 to 2 pi was 7 pi over 6. And I know that if I added or subtracted 2 pi, that I would find other solutions. Okay, so I'm going to take my first solution, 7 pi over 6, and I'm going to add its period, 2 pi, times n periods. And one thing to note is that n will always be an integer, okay? It's always going to be 1 or negative 1, or 2 or negative 2. No decimals. Okay, so that's one solution. The other part of that solution would be the 11 pi over 6. And if we add its period, whether it's in the positive or negative direction, that's going to get us to other solutions. So this would be my general solution. So you can think of general solution very similar to coterminal angles, right? Coterminal angles, we have to add 360 or subtract 360. Okay, same thing with the general solution. Okay, the other method graphically is to use the intersection method. So that means we have two graphs. So your y1 would be the left-hand side of the equation, sine x, and your y2 will be the right-hand side of the equation, negative 1/2. Alright, so this would be your y2. And your y1 would be the sine function. So now that we have our two graphs up there, if you were thinking about the intersection method, what would be your solutions? Right? You have two graphs. You're looking for what values of x would satisfy this equation. The first method, we use the x-intercept method, and we're finding x-intercepts. Now we're using the intersection method. Our solutions will be the intersection points. Okay, and this is something you guys looked at in grade 11. Okay, and obviously we're going to get the same solutions as we did before. So negative 5 pi over 6, negative pi over 6, 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6. And just keep in mind the pairs of solutions. So here we're differing by 2 pi, which signifies a period. Okay, and 11 pi over 6 differs by 2 pi for the solution circled in red. So now that we've gone through a pretty guided example, let's try another one. Okay, we're going to solve this using two graphical approaches. Okay, the equation we're looking at is cosine x minus 0.75 equals 0. And our domain is x is an element of all real numbers, which means we have to find the general solution. Okay, we're not just finding solutions between 0 and 2 pi anymore, it's the general solution. Okay, and we need to give our answers to the nearest hundredth of a radian. Before we do that, I'll just summarize some of the steps. We can basically graph this by using the intersection method or the x-intercept method, or zero method. And then we determine our general solution by just adding the period to those solutions. Okay, so Jose, what method would you like to use? The intersection method or the x-intercept method? We're going to do both, so it doesn't matter. Intercept. Okay, so that means we need a y1 and a y2. So if we're starting with cosine x minus 0.75 equals 0, we need to move this 0.75 to the right-hand side. So y1 will be cosine x, and y2 will be 0.75. So what you'll want to do is, let's just put our window settings, sorry, I gotta start this over. Put our window settings between 0 and 2 pi on the x-axis. And if you take a look at the graph that's on your page, what's it scaled up by? Pi over 6? So I'll just show you how you figure that out. So here's pi. There's 1, 2, 3, 4, 5, 6 spaces between pi and 0. So each little tick for scale is pi over 6. Okay, and let's put our y min to -2, y max at 2. You guys probably already have this in there. And scale 0.5. And then we'll graph cosine x. And my y2 is 0.75. So if we're using the intersect method, our solutions will be the intersection points. So we're going to be tracing what's the x-coordinate here and what's the x-coordinate there. So second trace, number 5 for intersect.
0, 2, 5,
Just get nice and close to that intersection point, press enter 3 times, and we're getting 0.72. That's the nearest hundredth. Okay, so I found 0.72, that's to the nearest hundredth. Now I'm going to find the next intersection point. Second trace, 5. Move the cursor all the way over. Get nice and close, and then press enter 3 times. And you get 5.56. So before I move any further, any questions on graphing or solving for those intersection points? Do you guys have questions? Joe, did you have?
Like, why do you put the 0.75 in the other thing and don't keep it in the whole equation?
So if I was using the x-intercept method, everything would be on the left-hand side like we started, and that would be your y1. And you'd be looking for x-intercepts. But here you said the intersect method, so that means you need 2 graphs that will intersect each other. So I took this negative 0.75, I added it to the right-hand side, and got 0.75. So my y1 is the left-hand side of the equation,
Yeah.
and my y2 is the right-hand side.
Okay.
We're going to go through the x-intercept method too, which you might prefer, especially if the equation's given that way.
Okay, sounds good.
Okay, so we have x equals 0.72 and x equals 5.56. If I were to find the general solution, that means that the domain is going on forever. Okay, so this cosine wave is just going and going and going and going. So I'm going to take my x-intercepts and I'm just going to add the period times n. Okay, so the general solution will be x equals 0.72 plus 2 pi n and 5.56 plus 2 pi n, where n is an integer. Okay, so that's the intersection method. Now we're going to use the x-intercept method, or the 0 method. So instead of having 2 graphs, we're going to have just one. So subtract 0.75. And then graph it. And so, Joe's this method, we only have one graph, there's no intersection.
Okay.
And we just trace the x-intercept.
Yeah, I just didn't understand why you took the 0.75, but not get it.
there's going to be some equations that you see that it's going to be much easier to just look at the intersection points. There's going to be other graphs where it's much easier to find the x-intercepts. Okay, as you can see with both graphs, it's pretty easy for this type of example. And these are methods that you can use when you're solving radical and rational equations too. So just keep that in mind. I feel like we've reviewed how to find x-intercepts. You are going to get the exact same value, 0.75, 5.56. Okay, that's where we're crossing the x-axis. We would have to add the general period of 2 pi n to get the general solution.
So for this for 10, for those solutions, you would put 0.72 plus
Pi, yeah. Okay, and we're going to do a few tan examples coming up. So if you guys didn't hear that, Emily brought up a good point. We've been looking at the graphs of sine and cosine. Their periods are 2 pi. But if this was tan, we would have to add for our general solution just pi n. Okay. So let's look at how to do this algebraically. So the first thing you want to do is make sure that you have your trig ratio isolated. So we need to get cosine by itself. So I'm going to add the square root of 3 over and then divide by 2. And that gives me cosine x equals the square root of 3 over 2. Okay, now cosine, using my cast rule, in step 1, I'm going to figure out where do we have a positive ratio. That's going to be in quadrant 4 and in quadrant 1. So I'm going to have solutions in quadrant 1 and 4. Okay, second step is you need to find your reference angle. Okay, cosine, that's the x-coordinate, right? So if the x-coordinate on a special triangle is root 3 over 2, do you guys remember your special triangles? What's your reference angle? 30, good job. Okay, or if you forget that, you can always just go second cosine, root 3 over 2, and you'll get your reference angle to be 30 degrees. Okay, so you can remember your special triangles or just use your calculator. Now we need to apply our reference angle in quadrants 1 and quadrant 4. So in quadrant 1, okay, I think that one's fairly straightforward. Our solution will be 30 degrees. Okay, and in quadrant 4, our reference angle is 30. Our rotation angle will be 330 degrees. So we're going to go 360 minus 30. Now, an important thing to do is read the question, telling us that x is a radian measure. So although I've solved for this in degrees, I can just translate this to radian now. So 30 degrees is pi over 6, and 330, just confirm for me, 11 pi over 6. Okay, so those are our two solutions between 0 and 2 pi within the period of cosine. Okay, but our general solution will be when there's no restriction on the domain. It's going on forever. X is an element of all real numbers. So we're going to take pi over 6 and add 2 pi n, and then 11 pi over 6 plus 2 pi n, where n is an integer. And we're good. So we've been looking at sine and cosine. It's important to know these steps though, because if this were tan, solve the equation where the domain is 1 period. So for sine and cosine, we need to look at all 4 quadrants, because the period is all the way to 2 pi. If this were tan, we would only be looking at the first 2 quadrants, because the period of tan is 180 degrees. Okay, and then step 2, we just need to add or subtract multiples of that period to the solutions. The next example, you might have some general solutions that can be combined together. So let's just go through the same process and then we'll talk about the solutions at the end, how they can be combined. Okay, so if we have sine x equals 0, that means we have solutions in all 4 quadrants. Okay, because sine is positive and negative. Step 2, we need to find our reference angle. Okay, and if we go second sine 0, our reference angle is 0 degrees. And if you think about your unit circle, you can apply that knowledge too. Sine, it's actually the y-coordinate, right? On your axes, where is y going to be 0? Along the x-axis, right? So at 0 degrees, 180 degrees, and 360 degrees. Okay, because we have the point 1, 0. So the sine value, y is 0, and we have the point negative 1, 0. The sine value is 0. So you can think about that, or we can just take our reference angle 0 and apply it in all 4 quadrants. 0 plus 0, 0. 180 minus 0, 180. 180 plus 0, 180. 360 minus 0, 360. So our solutions within 0 to 360 are 0 degrees, 180 degrees, and 360 degrees. And in radians, actually let's just ignore that for a second. Let's talk about how these solutions can be combined. Would you guys notice the difference consistently between all 3 solutions? 180. So our general solution will be 180 degrees plus the period n. Okay, so just keep in mind in radians this is 0, pi, and 2 pi. But there's a difference of pi there. So the general solution will be pi plus 2 pi n, where n is an integer. Okay, that solution is always going to be separated by 180 degrees.
And just pi n.
I guess the only thing I'm thinking, I guess you could do that. I was thinking about the 0 degrees if that would change it, but I guess if you did 0 rotations, then it could just be. Just want to make sure. I don't see why not, because really it's all divided by, all the solutions are separated by 180 degrees, so if it's 180 degrees, you could just go pi over n. So even more simplified, pi over n, where n is an element of integers.
Wait, so it's just pi.
Yeah.
Well, makes sense.
Okay, so a more combined solution would be just pi n. Now let's look at cosine x equals 0. Okay, again, we're looking in all 4 quadrants, because 0 is positive and negative. Then we need to find our reference angle. Okay, and if cosine is 0, that means x equals 0. We should be at 90 or 270, but I'll just go through this. So second cosine, 0, you'll get a reference angle of 90 degrees. So apply 90 degrees into all 4 quadrants. Let's figure out our solutions. 0 plus 90, 90. 180 minus 90, 90. Okay, 180 plus 90 is 270, and 360 minus 90 is also 270. Okay, and if you think about cosine, if cosine x equals 0, remember that cosine is the x coordinate. Well, the only x coordinates where you're going to have 0 would be at, on the unit circle anyways, would be 90 degrees or 270 degrees. So it's just a little shortcut, but you can always find your reference angle if you forget. Second cosine, 0. Okay, so we figured out our solutions to be 90 and 270 degrees. What's the difference between those? 180. Okay, but it starts at 90 degrees. So we have pi over 2 plus pi n, where n is an integer. This is our general solution. Okay, and I'll actually just talk about that a little bit more. If you go 90 plus 360, what do you get? 90 plus 360?
150.
Okay, thank you. 450. And what is the difference between 270 and 450? 180. Okay, if you went 270 plus 360, you get the next value. What is that? 630. Okay, and if you were to take the difference between 450 and 360 or 630, you should get 180 degrees again. So you can see if you did it, you went further in your solutions, all these solutions are separated by 180, starting at 90 degrees. Okay, so we have 90 degrees plus pi n as your general solution. Sometimes when you're solving these, you're going to be asked for solutions within a restricted domain. So it's pretty much the same thing except for you're applying your general solution until you get within the domain specified. Okay, so we have 2 sine x minus the square root of 2 equals 0. First step. Jared, Xander, not paying attention, are you? What's the first step? Well, you want to isolate the trig ratio. So we have sine x equals the square root of 2 over 2. Now, if you guys have memorized your unit circle or your special triangles, what's the reference angle? 45. Good. Your reference angle equals 45 degrees. Maybe I'll just put reference x, because we're in terms of x. Okay, and sine is positive, so we're going to be in quadrants 1 and quadrants 2. So applying 45 degrees in quadrant 1, my initial solution will be 45 degrees. And in quadrant 2, 180 minus 45, we get 135. Do those solutions fit between 360 and 720?
Yeah. No.
No. So what am I going to have to add to these to get within that domain? Add 360. So why don't you guys do that until you get solutions between 360 and 720. So 45 plus 360. So 45 plus 360, we get 405 degrees. And 135 degrees plus 360, we get 495 degrees. Now, let's see if we can go further. Okay, if you add 360 to 405, will we be outside of the domain? Yes, and it's the same if we added or subtracted from 495. Okay, so this would be our final solution within the specified domain. I think we will have time. My clock's a little quick, so I want to make sure we do a tan one as well. So, Xander, Jared, first step. isolate the ratio. So we have cotangent x equals negative 1 over root 3. Okay, and just to make life a little bit easier, I'm going to turn this into tan. So the reciprocal of cotangent is tan. And if I'm going to make this a tan ratio, I just take the reciprocal of the ratio itself. So I get negative root 3 over 1. So, if we read through the steps here, determine the period of the trig function. What's the period of tan? 180. So I'm not going to even look at quadrants 3 and 4. I'm only going to look at solutions between 0 and pi, or 0 and 180. Then I need to solve the equation between 0 and 180. So if tan is negative, I'll just draw out the cast rule. If tan is negative, we're only looking in quadrant 2. Okay, if we were looking at all 4 quadrants, it'd also be quadrant 4, but we only look within the first period. So tan x equals negative root 3. Let's just find our reference angle. So second tan root 3, don't include the negative. Thank you. So we get 60 degrees. Now we need to take that 60 degrees and find a solution between negative 180 degrees and 0 degrees. So, 60 degrees, let's take it back 180. Okay, what's the period of tan? 180. So that's why I'm going to take my solution from quadrant 2 and I'm just going to go backwards. So just like we added and subtracted 2 pi, now I'm just subtracting pi. So I get negative 120. Okay, if I subtracted another 180, I would be outside the domain. So my solution is x equals negative 120 degrees, but the domain's in radians, so I just have to convert this now to radians. So 2/3. And, sorry, don't forget it's negative 2/3. Okay? So hopefully that was a little bit of review. Well, thank you, Emma. Good luck, everyone who's on the road tomorrow, tonight.